Hi, everyone, and welcome to online lectures 17 and 18. Today we'll be discussing experimental design parts 1 and 2. Okay, so we've been talking about measures, reliability and validity of measures. Then we talked about validity of studies and even control techniques for studies. But what we have not talked about today is the actual design of the study. So what is the design? The research design is the outline, the plan, the strategy. Okay, and the purpose of a research design is really to control for unwanted variation. It also suggests how the data will be statistically analyzed because certain designs go or are paired with certain statistics. So when we're thinking about the goal of our research design, we should be trying to choose the strongest design that is ethical and feasible. Okay, so we have to keep both of those in mind because sometimes we're doing a study that is very interesting, but yields a weak research design, and that's perfectly fine. Okay, so let's start with some weak experimental designs. These are designs that do not control for many extraneous variables and provide weak, if any, evidence of cause and effect. They lack a comparable control group. Okay, so they may have a control group, but it's not exactly going to be guaranteed to be comparable because we're not necessarily going to have that randomization that we'd like to have. Okay, so let's start with the one group post-test only design. Here, a single group of participants is given the experimental treatment condition followed by the post-test measure. Now, almost all threats to internal validity apply. So suppose we want to institute a new reading curriculum. We do this as our treatment, and then we look at people's reading ability after we have instituted the treatment. Okay, let's say that their reading ability looks to be high after they have had the treatment. Well, how is that helpful? Do we know that the treatment actually had any influence on the post-test measure, on the post-test at all, on their reading? No, because we don't know what their pre-test scores were like. We don't know what another group would have looked like who didn't have the reading intervention. So we don't have a control group here. We don't have a pre-test here. And because of these reasons, this type of design is rarely used. It's really not that common. And almost all threats to internal validity exist here. Okay. So let's improve upon this a little bit. Let's go to a one group pre-test post-test design. Now this is where you have a single group of participants that are given a pre-test, then the treatment condition, then the post-test measure. Now this is a little bit better because we can at least compare pre-test to post-test. But it's still not perfect. There's still many threats to internal validity, and it's still very difficult to claim causality. So let's look at this example of a one-group pre-test post-test design. In this example, we have students whose reading is measured at the beginning of the school year. Then we give these students a new reading curriculum during the school year, and then we measure these same students' reading at the end of the school year. Okay, so pre-test, we measure their reading. Treatment, they get the reading curriculum. Post-test, we measure their reading again. Now, I want to point out the X's and O's here because we're going to continue to use these. The O is when you give a measure or an assessment, and the X is when you give a treatment. So like we said, there are many threats to internal validity here that we're just not accounting for. Think about history, testing, regression, instrumentation, and maturation. All possible threats here. And let's consider this particular example. So if they actually improve from pre-test to post-test, and the researcher wanted to claim, oh, my treatment, my new reading curriculum caused the improvement, could you pose an opposing argument to this? Well, I suspect you could. I suspect you could say, well, we don't know. Maybe there were other things going on at the same time that could have influenced from pre-test to post-test. First of all, just being given the measure might have given them some practice. They might have had some maturation in their reading ability, right? That maybe was not related to simply just the treatment. So a lot of possibilities here besides just the treatment. So weak evidence of cause and effect, weak to no evidence of cause and effect. Okay. So now I want to introduce one term to you. It's called between participants designs. And it's basically when each group is exposed to different levels of the independent variable. Okay, so now we're going to have more than one group. And we're going to have typically one group get a treatment of some sort, another group that serves as a control, something along these lines. That's a between participant design. Okay. So let's look at another weak experimental design, but now we're adding in the between component, right? So we have a post-test only design with non-equivalent groups. This is a design in which the experimental group is compared to a non-equivalent control group at the post-test. So the problem is there's no assurance that the groups were equal at the beginning of the study because they were not randomly assigned. So you could wind up confounding selection with treatment effect. Okay, let's look at this example to understand this better. Now we have our experimental group, which is School A, that opts to add a new reading curriculum. As our control group, we have School B that opts or chooses to use the old reading curriculum. Both schools post-test reading at the end of the year. So just to get our symbol straight, notice how the experimental group, the treatment group gets the X. This one does not get any symbol. And then we're doing the assessment, we got the O's here. And we compare their measure at the end of the year. Okay. So again, this is better, right? Because we have another group now, but we don't know if they started off being equal. We don't have necessarily a comparable group. Or even if they started being equal, maybe they have a reason to develop at different rates, aside from the new reading curriculum. See, we just didn't get our groups randomly assigned here. And so that's the weakness here. Okay. Now let's turn our attention to some strong experimental designs. These are designs that effectively control extraneous variables and provide strong evidence of cause and effect. We're going to have improved internal validity. Remember, that's related to cause and effect by eliminating rival hypotheses. We're going to have a control group like we did in the last example, but now we're also going to use random assignment. Remember, random assignment is very, very important for internal validity. So that's a big improvement. Okay. So let's talk now about the post-test only control group design. This is very, very similar to the design we just talked about, except now we're randomly assigning people to groups. So we'll increase the likelihood of equivalence across our groups. The use of a control group eliminates most threats to internal validity. Now, one weakness you could pick on is that there's no guarantee that the groups are equivalent, right? I could random assign my heart out, and the groups could still wind up not being equal, just due to luck of the draw. But for the most part, random assignment works. And for the most part, it will assure that you get equivalent groups. Okay. So here is our post-test only control group design example. We have a sample of research participants that we randomly assign to our experimental group or our control group. And in this case, we're going to talk about social skills training. The experimental group receives the social skills training, marked with the X. The control group receives no social skills training. And our DV of self-confidence is measured at the post-test for both groups. So now, because we did randomly assign our groups, we have a much better chance of being able to attribute the treatment to the result. So in other words, now, if our experimental group performs much better on the post-test measure, displays larger levels of self-confidence, we can probably attribute that to the treatment because they were randomly assigned. One got the treatment, one didn't. And when we look at the post-test, we can say, look, this is probably due to the treatment. Okay. So if you think that this sounds very, very similar to the post-test only design with non-equivalent groups, it really is. It's really practically the same thing, except with the post-test only design with non-equivalent groups, we did not randomly assign. Here we are randomly assigning. Okay. Now, I will share with you, it's not always possible to randomly assign, right? What if I'm comparing people who report different genders? Well, I can't assign people to a particular gender. Or if I'm comparing people in different age groups, again, I can't assign people to be a particular age. You be in the younger group, you be in the older group. That doesn't work. It's only when we have situations like this, where we have something like social skills training that we can randomly assign, that we can think about doing the post-test only control group design. So I want to point out that even though the post-test only design with non-equivalent groups is considered a weak design, we use it a lot. And it's okay, because those studies are still interesting. But if we have the ability, we prefer to use this design, the post-test only control group design. Okay. Post-test only control group design with 3 groups is basically the same thing, except now we might have 2 experimental groups who get 2 different types of social skills training, right? And we might mark that by X1 and X2 and have 1 control group. And then we give all 3 the measure of self-confidence at the end. Still have our random assignment. Okay. So now let's switch gears to within participants' designs. In this case, participants are included in all conditions. This is also known as repeated measures designs. We talked about this some when we were talking about control techniques, right? And we talked about counterbalancing. So now let's talk about the within participants post-test only design. All participants receive all conditions, and a post-test is administered after each condition is administered. So let's talk through an example of this. Participants in this case are going to be elementary school children, and we're going to look at 3 different breakfast types. We're going to look at cereal, oatmeal, or no breakfast. And each child has each breakfast type on 3 different days. And our dependent variable is going to be cognitive performance, a series of cognitive tasks that the child is to complete after breakfast. Okay, so what does this mean? This means that on one day, one child will get cereal, next day oatmeal, next day no breakfast. Now we might have, to counterbalance, we might have other children take this in a different sequence. Maybe another child has oatmeal the first day, then no breakfast, then cereal, right? So we could have 6 possible sequences because we have 3 different groups, cereal, oatmeal, and no breakfast. So we might counterbalance this and have people do different sequences, have different children do different sequences. But in either case, the idea is that each child experiences the cereal condition, the oatmeal condition, and the no breakfast condition. Okay. So what is the strength of this? The effects of individual differences are controlled, and fewer research participants are needed. So these are 2 very important strengths. Because we are only comparing people to each other, we really reduce a lot of the error that comes up when we are comparing people to different people. And because of that, you can get by with less research participants. Now, what are the weaknesses? Well, it's difficult for participants, right? They have to be in all parts of the study. It takes longer for them. It would be so much easier if they could just be in the cereal condition. And also there's a potential problem of differential carryover effects. Now, this is particularly problematic with medications. If medication A carries over and interacts with medication B, more so than when it's followed by medication C, that could be a real problem. I don't expect that potential differential carryover to happen as much with the different breakfast types, but who knows? Maybe. Okay. So now let's talk about a mixed design. Okay, this contains both between participants and within participant variables. And an example of this is the pre-test, post-test control group design. So we're taking the post-test only control group design that we already discussed, and we're just going to add a pre-test to it. Participants are still randomly assigned to groups, and each participant has the same pre-test, gets different experimental conditions, and then has the same post-test. Okay. Here's an example. Here's our pre-test, post-test control group design. In this case, we have all of our participants getting our pre-test measure. Then we can randomly assign them to the control group or the experimental group. If they're being pre-tested, let's say for social anxiety, then 50, if we have 100 people, maybe 50 will get the treatment for social anxiety, 50 do not get the treatment for social anxiety. Then we post-test them once again for social anxiety. This is kind of a neat measure, a neat design, because we've got both a within measure and a between measure. Within, in that they're getting both pre-test and post-test. Between, in that some people are getting the treatment and some are not getting the treatment, and that is randomly assigned. Okay. So what are the advantages of including a pre-test? Well, you can assess the effects of randomization. See, that's what we were worried about before. Remember, we were worried that even if we randomize the groups, we can't guarantee that they were equivalent at pretest. Well, now we can find out if they're equivalent at pretest. We can assess for ceiling or floor effects. And in other words, we can assess if there's an issue of everyone starting off with extremely low levels of anxiety or a floor effect. So we wouldn't expect them to get much lower. Or in the case of, let's say, reading ability, maybe there's a ceiling effect and everyone starts off really high on reading ability, so we can't expect them to get much higher. We can also statistically control for pretest differences, and we can assess the change in our dependent variable from pretest to post-test. So lots of advantages. What's the disadvantage? Well, again, it may not generalize to situations with no pretest. May not generalize to situations with no pretest. Okay. All right. So now let's turn our attention to factorial designs. This is when you have two or more independent variables that are studied to determine their separate and joint effects on the dependent variable. These can include only between participants variables, only within participants variables, or both between and within participants variables. The key here is that we're going to have two or more independent variables. Okay, and we've not really discussed that to date. So let's talk about it a little bit. Okay, so the best way to really understand this is through an example. Okay, so what we're going to do is look at this example of how sleep deprivation and caffeine consumption affects our ability, maybe our performance in a driving simulator. Okay, so we're going to test sleep deprivation and caffeine consumption. So as you can see, we have two levels of sleep deprivation, deprived and not deprived, and three levels of caffeine consumption, low, medium, and high. And then you see in these cells below, we're really going to wind up with 6 groups. People who are low on caffeine consumption and are either not deprived or deprived, medium with not deprived and deprived, and high caffeine consumption, not deprived on sleep and deprived on sleep. So we're going to have these 6 groups. So what we're going to want to do is start to understand what kind of effects we may have here. For example, we may have what's called a main effect. It's the influence of each independent variable on the dependent variable. And there's one main effect for each IV in a study. So what does this mean? Let's go back. In other words, we're asking the question for main effects, does sleep deprivation make a difference? And we're asking the question, does caffeine consumption make a difference? Okay. So we're asking one main effect question for each independent variable that we have. Okay. Now, we also have what's called interaction effects in factorial designs. This is the joint or interactive effect of 2 or more IVs on the DV. And it's when the effect of one independent variable depends on another. Graphically, an interaction yields non-parallel lines. So in this case, maybe it's not so straightforward as to whether caffeine consumption and sleep deprivation independently have an impact on driving performance. Maybe we need to go a little bit deeper. In other words, oops, let me go back here. In other words, what if it's the case that those who are sleep deprived benefit more from the more caffeine you give them, but those who are not sleep deprived don't do so well on caffeine? What if there's a combination, an interaction between these variables? Well, that's what we talk about. That's what we mean when we're talking about interaction effects. It's when I ask you, so is there an effect for caffeine consumption? And you have to answer me, well, it depends on whether they're sleep deprived or not. Or if I ask you, is there an effect for sleep deprivation? And you'd have to answer me, well, it depends on how much caffeine they've had. Okay. So let's look at some results. So here we have the results. These are the means for each group. And if we want to compare sleep deprived to no sleep deprived, we compare the average mean. If I take the average of 3.1, 9.7, and 3.5, I'd get 5.4. Okay, and I'm assuming there's equal number of participants in every group here. And same here. If I take these averages, I'll get 4.4. If there is a big difference here, big enough, we'll just say big enough because we're not going to worry about the statistics for this. If there's a statistically significant or big enough difference here, then there's an effect for sleep deprivation. Now it looks here, we'll assume this is big enough that being not deprived of sleep, yields more correct maneuvers, more correct driving maneuvers. Now here we look for the main effect of caffeine, and we do the same game. We take 3.1 and 1.3, 9.7 and 4.9, 3.5 and 7.1. We take those averages, and we see, it looks like medium caffeine consumption gives you the most correct driving maneuvers. So if I just looked at these results alone, I'd say, okay, so don't be sleep deprived when you drive and have a medium amount of caffeine when you drive. But there's more to this story. Let's look at this graph. This is the interaction between sleep deprivation and caffeine consumption. So let's start by looking at our not deprived sleep group. Okay, so a low amount of caffeine doesn't really do you so good, and a high amount of caffeine doesn't do you so good. Yeah, it's that medium amount of caffeine, just like what we saw before, that helps you the most with your driving. However, now let's look at the deprived group. Looks like the more caffeine you give the sleep deprived group, the better off they are. The more caffeine you give them, the better off they are. So it's not such a simple answer. It's not just medium caffeine. It depends on sleep deprivation. Now, I will observe that even giving the highest amount of caffeine to the sleep deprived group, they're still not performing as well as the group that's not sleep deprived with a medium amount of caffeine. That's kind of interesting. However, main point is one of these main effects depends on the other. And when you see an interaction like this, if you have more than one IV, you tend to report the interaction more so than the main effect, because this is the really interesting part. So again, can't just say it's medium caffeine consumption because it really depends on the level of sleep deprivation. Okay. So let's talk about some different factorial design notation. You could have a 2x2 design, which means the number of numerals represents the number of IVs. So because this is 2x2, it means there's two different independent variables, just like in our last example. Now, each number indicates the number of levels for each IV. IV1 must have 2 levels, and IV2 must have 2 levels. So if in our previous example, caffeine only had 2 levels, we only had low and high for caffeine, well, then this would be the appropriate representation of that design. However, because sleep deprivation had 2 levels and caffeine had 3 levels, this is actually correct, 2x3 design. 2 numbers, so 2 IVs, sleep and caffeine. IV1 had 2 levels, sleep, not deprived and deprived. IV2 had 3 levels, low caffeine, medium caffeine, and high caffeine. And again, if we added a third number here, 2x3x2, that would mean we had 3 IVs, and the third IV would have 2 levels as well. Okay, so that's a little bit about factorial design notation. Let's talk a little bit about the strengths and weaknesses of factorial designs. Strength. Having more than one independent variable allows for more precise hypotheses. Right? I can actually not have to just talk about one independent variable. I can say how others might impact or interact with that IV. I can also control extraneous variables by including them as an IV. Remember, we talked about that a little while back. So if I was concerned that sleep might be this extraneous variable getting in the way of my measuring caffeine and driving the performance, I can include it as an IV. And I also have the ability to find interactive effects. I also have the ability to find interactive effects, just like we did with sleep and caffeine. Weaknesses. Using more than two independent variables can get cumbersome, right? Having that many groups, we already had 6 groups when we had 2 IVs with 2 and 3 levels. Add in another IV even with only 2 levels and we're up to 12 groups. That's getting to be a lot. And also higher order interactions when there are more than 2 independent variables are very difficult to interpret. They get really challenging. Okay. All right. So at the end of the day, how do we choose? How do we construct the appropriate experimental design? Well, one thing we can use is prior research literature. That can really guide our choice of design. That can be really, really helpful. It also depends on the research question. Again, if you're asking a question about a variable that you cannot manipulate, that you cannot randomly assign, you're going to be stuck with a weaker experimental design. And again, as I said, that is perfectly fine. So your research question really has a lot to do with the design, but you should always choose the strongest one that you possibly can. Okay, so that is all I have for you guys for today. Be well, take care, and I will talk to you next time.